Hi everyone, so I'm continuing from where I left off in the first part video. So the question was, why does a soda get flat when you leave it open? Okay, so if you've ever had a can of soda before, when you open it, you often hear that psst noise, and that's the carbon dioxide escaping, okay? So there's carbon dioxide, which is a gas dissolved in water, and then soda is just added like syrups and flavoring. So when you open a can of soda, some of that carbon dioxide is going to escape. If you leave it open for a long enough period of time, that gas will keep escaping. And then the soda gets what we call flat because it's lost its carbonation. Basically, that carbon dioxide is no longer dissolved in the liquid. So now let's talk about the relationship between solubility, so something dissolved in something else, and pressure. So pressure can affect solutions such as a gas, solute, and liquid solvent. So again, like CO2 dissolved in water, and then again, soda, there's just additional like syrups and flavoring to make it soda. Otherwise, it's just sparkling water. Okay. So when a bottle or a can is unopened, that pressure inside of it is generally pretty high. And because it's high, that carbon dioxide is staying dissolved in the liquid. Versus the moment that you open that soda bottle or that can, you're going to decrease the pressure. So the pressure is reduced or decreased. Basically, it's lowered. So now that carbon dioxide that was dissolved in the liquid solvent is going to escape. So if you have less pressure, that means less soluble, meaning that carbon dioxide is no longer going to stay dissolved in the liquid, okay? So that's why it gets flat when you leave it open for a very long time. So now we can look at the relationship. Now we start to understand the relationship between pressure and solubility. So what type of relationship is this? Well, if we as pressure increases, I should say, so when the pressure is really high, when the can or the bottle is closed, that means that the solubility is also really high and increases. Versus when we open, right, when we open that can or bottle, the pressure will decrease, and then that solubility will also decrease. So this is what we would call a direct relationship. Just like when we talked about Charles' law and Gay-Lussac's law with pressure and volume, and then pressure and temperature. Pressure and temperature, and then temperature and volume. Boyle's law was pressure and volume, which is an indirect relationship. So the solubility of a gas in a liquid, to be specific, increases, or directly, I should say, is directly proportional to the partial pressure of the gas on the surface. This is also known as Henry's law. So to illustrate that in terms of a, we'll get to this in a second, a graph that would look something like this. So as the pressure increases, so does the solubility. As the pressure decreases, so does the solubility. And again, this is specific to the example of having a gas solute and a liquid solvent. Okay. That's the type of relationship we're seeing between pressure and solubility. It's going to be direct for this situation. All right, now let's look at temperature and solubility. Okay, so in this situation, in these two graphs, you can see that you can see a couple different things here in terms of substances. So again, these are when we have a gas solute and a liquid solvent, to be specific to what we're talking about. All right, so looking at these graphs, think about the type of relationship you're seeing. Is this a direct or an inverse relationship? Okay. So you can see as the temperature is going up, the solubility is going down in both of these graphs, okay? So, and both graphs also look like this. This is an inverse relationship. So as the temperature increases, the solubility decreases for a gas solvent or gas solute in a liquid solvent. So the two variables that were on the graph were temperature and solubility. What type of relationship? This is inverse. Okay, so it's when we have this going on, like we saw in Boyle's law with pressure and volume. In those situations, we were just talking about gases. Now we're talking about solubility, which involves two things. What are the solutes and what are the solvents that were represented in the graph? So the solutes had to be the gases. Okay, so that was S2 in the graph, H2S, CO2 and O2, versus the solvent is water, which is H2O. Okay. All right, so this is actually why, if you, like, that's why you actually want your soda, okay? This is why you actually want it to stay cold instead of hot. This is, if you actually, colder, I know this sounds weird because people might argue like cold soda versus room temperature soda. Cold soda is more carbonated than hot, or like if it's at room temperature, warmer soda. And that's because of this right here, okay? If you have a soda that's cold, okay, cold, you're gonna have a higher solubility, okay? Versus if you leave a can of soda, let's say unopened, and you're leaving it at room temperature, that it's probably when you go to open it, it's gonna make a more psst noise because that gas isn't staying dissolved in it, okay? In a can of soda, there is some space here, okay? So if you have a cold can, well, you're not going to have much of that going into this space. Versus if you have a can that's warmer, you're going to have a lot of CO2 in this space because it's not staying dissolved in that liquid. So it's most likely going to start building up here. So when you go to open it, it makes a really loud psst noise versus when you open a can when it's cold. So pay attention to that next time you're opening a can of soda at room temperature versus when it is cold. All right, so now let's look at temperature for solubility versus temperature of a solid solute and a liquid solvent. So pretty much what we're going to be focusing on for a lot of this unit. So you can see on this graph, we generally have a trend going this way. And this makes a lot of sense. This is pretty intuitive for most of us. So the two variables on the graph are temperature and solubility, just like the last one. But we're seeing a direct relationship on this graph. And that is because the solutes are solids. Okay, so they had KNO. So a lot of these are ionic compounds. So instead of NaCl3 or NaCl like sodium chloride, we have RbCl. And then the solvent is water. All right, so, and this makes a lot of sense. Most of us, like if we're talking about like salt, NaCl, in let's say a cup of water, we know that it would dissolve faster if we were to heat it up. Like it would be more soluble. It's kind of the same thing like if you put sugar in coffee, it's going to dissolve more easily in hot coffee than it is in cold coffee. So again, this is for a solid solute and a liquid solvent. This situation up here was for a gas solute and a liquid solvent. All right, so then we can look at how certain things affect the rate of which a solute dissolves. So we already know that if you increase, okay, and again, this is for a, solid solute, liquid solvent, okay, so like salt in water. We already know if you increase the temperature, the molecules will move, remember kinetic molecular theory, faster, and thus they'll come in contact with each other more, and this is also speeding up the process of a solute dissolving. So the reason that something's going to dissolve faster in like hot versus cold is because the molecules are going to move faster. So it's not a chemical reaction, but it's that the molecules will be able to be broken down faster in the solute. Also, the surface area matters as well. I know some people might use sugar cubes in their tea versus like granulated sugar. So actually, the more surface area that you have, the faster the rate of dissolution or something dissolving. A sugar cube actually has less surface area, I'll just write SA for surface area, than something in a crushed or powdered form, like your typical granulated sugar, okay? This actually has more surface area, so more chances for the two things to interact with each other. And then also, of course, agitation. If you pour a bunch of sugar into your coffee, you're most likely going to stir it. You're not just going to leave it there. So that can help move the molecules around more to make them come in contact with each other more often. So to summarize, we talked about solutions in general. Okay, we're focusing on solutions, which are homogeneous, so things that are the same throughout. Mixtures. You have a solute and a solvent. The solute's generally what you have less of. The solvent's what you have more of. 99% of the time, our solvent's going to be water. And then there will be something dissolved in it, like an ionic compound, like salt, or maybe even something else like sugar. We talked about saturated, unsaturated, supersaturated, what that means. All the different examples of types of homogeneous solution, mixtures or solutions. Electrolytes versus non-electrolytes. And then we looked at some different relationships for solubility.